तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been looking into the design applications using FPGA board, and we also need different cards such as digital input output card in order to increase the resources. For example, we need the features of digital input output card are as follows. This is the card that we are going to use in addition to the IOs that are on the FPGA board. And the first feature is it has a total number of 48 discrete inputs and outputs, and each of these inputs outputs can be configured by the user, and therefore it is called user selected. And in addition to this, we have 4 push button switches, and each of which is hardware debounced. We use 7400 NAND gate for debouncing the circuit. This is right there on the board, and we also have 8 numbers of 4-bit binary switches and 8 numbers of BCD switches, and this is very handy if you want to straight away select in decimal values. For example, 0 through 9 are graduated on the BCD switches, and you can be at home with decimal settings, and if you still insist on a binary setting, you can use this one. In fact, all these 8 and 8 binary and BCD switches are in parallel. You can select one of the two, either one binary switch or one BCD switch which is connected in parallel, and in any combinations you can select them. In addition to this, we also have outputs, and we have some 7 segment LEDs, 6 numbers of them, and it has a right decimal point display, which is not available in the FPGA board, which we have already seen earlier. And in addition to these 7 segment LEDs, we have 16 numbers of discrete LEDs, and these are all the LEDs that we are going to use in the first application, namely the traffic controller. And this will be the very last of the 7 segment LEDs, and these 7 segment LEDs and discrete LEDs are once again in parallel. This is parallel in as far as the last 2 7 segment LEDs are concerned, and the whole board works on a single supply, namely plus 5 volts. And we will have a look at the layout of the IO card. This is the IO card which we see here. This card has a connector which is 50 position and a bug stick male has been put on this board, and naturally you need a female FRC connector to mate with this and interconnect it to the FPGA board on the expansion headers. We have 2 expansion headers, if you remember it right, and the cable will have to be bifurcated and then connected to the 2 expansion headers, and since this is only a single connector at this end, and we need to supply plus 5 volts, which is done through this. This is a male connector on the board. This is called a Molex connector, and normally this is popular for connecting power supplies. And first 2 pins are plus 5 volt, and next 2 pins are ground volt, and we also have some 3.3 volt provision here, and also some crystal oscillator, some 2 or 3 oscillators can be connected on the board, which is not shown here because for this particular application we are not going to use them. And in addition to this, we have push button switches, that is 4 numbers of them, and this is a push button shown here, and you also have some 4 jumpers here, and if you install the jumper on the left, right now it is shown as right install jumper. On the left, if you install, it will automatically select this push button switch, and it is debounced by using 74LS00, and you need cross coupled NAND gates, which we will be covering later on, and out comes the debounced digital value, which is connected to pin number 3 here. So this is the point which we are will have to connect, and second push button is connected to pin number 4, and pin number 5, pin number 6 respectively for PB3 and PB4. And in this fashion, all these switches, you see some more switches here, all of them are connected in the very same order, left to right, like a RAS scan order you can say. And we have parallel to these 4 bits, we have a switch SW1, which is a binary switch, and there will be naturally 4 discrete switches, and the leftmost of the switch is parallel to this switch here, and the second one is parallel to this, third parallel to the third position, and fourth one parallel to the PB4. And in parallel to this switch 1 is the BCD switch, which is SW5, and this is graduated, as I mentioned earlier, from 0 through 9, and you can use either the push button switch or this DIP switch for binary setting, or the BCD switch for the decimal setting. And all these are BCD switches, 4 numbers here and 4 numbers here down, all symmetrical, it is very easy to find. And similarly, SW9 through SW12, just as SW1 to SW4 is also a group of binary switches, 4 of them here, and totally you have each being 4 bits. In order to have cater to 8 numbers, you need 32 bits. So these 32 bits are connected in exactly the same order that you see in this fashion. First all these 4, and which is parallel to this 4, and then after this, so SW4 is connected to SW9 again in the same order. Once again SW13 is parallel to SW9 and so on, and SW16 is parallel to SW12, and this completes all the inputs, and they would naturally take 32 bits, and they are connected right starting from pin number 3, and counting 32 you will get land up somewhere here, and you can keep track of how many pins it is. It is exactly in the same order that we have seen the switch positioned here. In addition to this, we also have connected to the very same pins also this 7 segment LEDs. In fact, this very first, there are, if you notice, there are 6 7 segment LEDs. What is not shown in this figure is a decimal point, but we will be seeing that separately when we have a zoomed version later on. And that would mean 7 segment plus 1 for decimal point would take you 8 bits, and once again this is connected from pin number 3, as it is in the case of push button switch or SW1 or SW5, and the order in which this is connected is A, B, C, D, E, F, G, and then decimal point, in that order starting from the left. For instance, segment A is connected to pin number 3, segment B to pin number 4, and so on, and after you have exhausted all the pins for this 7 segment, which is 8 in number, and A segment for the second 7S2 will be connected next to that, immediately next to that, and so on in the very same order you will have totally. So, if you see 7 segment display, you have actually 6 into 8 including decimal point, that means 48 input outputs are available here. And if you notice this, we have a 50 pin connector, of which we need for VCC ground, that is plus 5 volt is connected to pin number 1, and pin number 2 is ground, am I right in this? And pin number 3 starts with this segment A, and it goes and until the very end 50. So, you can see that one difference is 2 if you knock them off, what you have is 50 minus 2, 48, and that is precisely what you have here. So, 6 into 8 is 48, and the very same order. In addition to this, we also have discrete LEDs, 16 of them. For example, this row you can see marked as LED 1 to LED 1, LED 2 and so on right up to LED 8, and here starts LED 9 through LED 16, and the first row LED 1 to LED 8 is connected in parallel to the last but one 7 segment, that is S5, 7S5 is connected to this one in parallel. That the LED 1 is connected to segment A, B segment is connected to LED 2 and so on, and right up to that. So, is the case for 7 segment S6, and A is connected once again to LED 9, B connected to LED 10 and so on, and decimal point will be naturally connected to LED 16, and these are all the resources that you need in order to do any considerable amount of application that you wish to have, and which is not adequate. I mean, the resources on the FPGA board is clearly not adequate for this purpose. And so, next what we will do is we will just have a look at the circuitry on the board. What we have here is a push button debouncing circuit, and this is a traditional NAND gate used. Instead of NAND gates, you can also use a NOR gate, and note that cross coupling is here. For example, Q bar is this output and Q is this top output, and Q is connected as the input for the next NAND gate, and this output Q bar is connected to the first NAND gate input here. This is a cross coupling, this is a traditional cross coupling, and the two other inputs of the NAND gate are this here connected to the push button switch. One of them is connected to normally open connection, and other is connected to the normally closed connection. Note that to start with, when you do not push any push button, and it will be returned to the ground, that is, this signal is forced to ground here. And notice also two pull up resistors used here. For a pull up resistor, a typical value is used is 4.7K or 10K. Normally these are all the industry standards, and if you use a higher value, naturally you can't guarantee the threshold level coming. It may be right at the so called high or low will be at threshold level, and so you avoid going for very high values. Don't go for megohms region as far as the pull up resistor is concerned, and typical value, as I mentioned, is around 4.7K, 10K. This has been proven in industries all over the globe, and naturally if you put smaller resistor and more circuitries, I mean similar circuitries involved, current consumption also will be more. So, accordingly you can limit this one by selecting 10K, or do not go beyond that 10K, and that is the price you may have to pay for. Otherwise, you will get into trouble as far as the noise performance, as well as the level of zeros and ones level will also give a problem. And so, to start with, let us see how this circuit works. And to start with, this one is in 1 because it is pulled high, and this is forced to 0. So, you know that 0 into anything is 0 here. So, just before the bubble of the NAND gate, you get only 0 here, and after the bubble you get 1. So, Q bar is 1 for this particular position of the push button that you have seen here. And let us see what is the case. This Q bar is connected as the input, just remember it is 1 here, and this is pulled high. So, 1 into 1 is 1 before the bubble, and after the bubble it is 0. That means, say it is 0 and 1 here. Therefore, we have used the notation Q and Q bar, because if it is 0 it will be 1, and if it is 1 it will be 0. and right now it is when the push button is not pressed, you get an output of 0. It is this where we are, we are going to take it as an output. And now let us see what happens when you press the button, push button. So this connection is broken, so it is going to travel all the way and strike at this point. Before that, what happens, let us have a look. Because the connection is broken here, this one which was forced to 0 will be 1, and because this is not yet connected to this ground, so that is also 1. So 1 1 would mean a store mode in an SR flip flop, and that is precisely we are exploiting here. And remember, it was 0 and 1, so this 1 was fed here, and 1 into this is still 1 only. 1 into 1 is naturally it is 0. So that is how the store mode is working. So in between it is always in a store mode, and here also you can analyze here, because it is 1 here and Q was 0 there, so it is naturally 1 here. So 0 and 1 are preserved, that is it is in a store mode. And now let us see when this button, this contact is made here, this is forced to 0 for the time being. So once this is 0, this will be 0 here, therefore 1 here. So the Q output has gone 1. Obviously I do not have to analyze this one, and because this will be inversion of this. So it has gone to 1 and this is gone to 0. Now what happens when you the switch strikes here, it will bounce back because of elasticity in any contactor. Any contact that you have, if you make, it will bounce back. So and this keeps on going for a while before it settles down. It will settle down because you are applying pressure to that, and so before that it will keep on making a number of makes and breaks here. So even during when it is made 0 here, we have already seen it is 1. So the very first time it has made a contact, even if it bounces back, it is in store mode. Therefore 1 is still preserved, and that is how it is debouncing. The circuit debounces very in a very simple manner. And so after like this, we have 4 push button switches, and naturally, and each LS not will have 2 packages, 2 such gates, and we need 2 such LS00. That is the reason why we saw in the layout earlier 2 number of ICs for 4 push button switches. So here for a binary switch, there are basically discrete switches here 1 to 4, and they are all grounded here, and there are other end of the switches returned to the IO pins in the order that we have already discussed, and each of them are pulled high by the resistor array. So is the case for a BCD switch. They are also resistor array. In fact, this resistor array and this are same, because all the switches are in parallel, and an on of a particular input switch input will return to 0 for obvious condition here. So it is grounded here, and this will be pulled low, and this is how you make a binary setting. And a BCD switch also similar to that, except that some inversion is involved. For example, if you put set 0 on the BCD switch, and the BCD switch is graduated from 0, 1, 2, 3 right up to 9. So that you can take a small screwdriver and turn that to any desired position. Thereby you can have a BCD or decimal setting. And this one, notice that one, for 0 you will be reading all ones. That means all the switches will be off. So all ones are read because of the pull-up resistor here, resistor array. And if it is 9, it will actually be reading 0, 1, 1, 0, because it will make a contact corresponding to 1, 0, 0, 1. That is the usual thing you can say. 1, 0, 0, 1 means making a contact is 1 here. So but in terms of logic, it will be inversion because of this configuration. So that is the reason why it is inverted here. And this one you know that it is nothing but 8421 code. So one can easily derive what you had to put here. Only remember to invert this. These conditions are required if you are to recode, and which may be given as an assignment towards the end. So now coming to this, a 7 segment LED is shown here, and the segments are all A, B, C, D, E, F. This is the last one, and in addition to that, a decimal point is also there, and the center one is the G. And typical circuit, driving circuit for this each of these LEDs, for that matter even the discrete LED, is quite simple. You have a 74 LS05, and that input is once again connected from the IO pin that we have already seen, 48 of them, and this is once again pulled high by a pull up resistor there, and when it is not connected, one will be pumped in here because of the this is a open collector output here, and thereby it can sink current, and the LED is connected in this fashion, and the LED, that 7 segment LED we are going to use, we have used on the board is common anode type. That is why for all the 7 segment are combined together as far as the common anode is concerned, and like that, and when it is 1 here, it will be 0 here, and this is the current limiting resistor, and naturally LE will conduct, and a typical resistance is around 200 ohms, which you can easily find. Conducting LED will take about 1.5 volt, and this will be 0.3 volt with reference to ground. That means 1.8 volt drop is accounted from plus 5 volt supply. The difference is going to be appearing across R, and you just allow for some 10 milliamps to 20 milliamps. Say a typical 10 milliamps is enough to light up the LED. We have this some of these FPGA boards, which will be showing one of the FPGA boards, especially based on XC4000 series. There are problems associated with this. This is a practical problem which we have experienced in the course of development of different applications, and the problem is FPGA boards using XC4000 series malfunction if input switches are connected permanently. See, we have already seen that in digital IO we have directly connected the switches, and that is to be used with the FPGA board XSV 800, that is using XCV 800 type of FPGA, and with that there is this problem is not encountered, and this problem is there only in the XC4000 type series, and the way to overcome this problem is by using on chip tri-state buffers as shown below. So, this tri-state buffers, there are you can, for example, this is the FPGA input pin, there you may be connecting to the external here a DAP switch. In such a case, if you do not use this tri-state buffer and straight away connect to the FPGA pin, and when you switch on and download the bit stream, the system really goes mad, it does not function, so it malfunctions, and in order to overcome that one, we have to either use an external tri-state buffer, or a better thing would be to use the onboard resources, and if you do this configuration, and the corresponding Verilog code for the same is given here, and it is a very simple Verilog code, and this is the module declaration, and A and B are what we have already seen, and enable is the enable for this, and this of course it is bigger here, you can remove this, actually it is enable there, and this is when enable is on, then A will be communicated to B, and A is will be connected to a DAP switch or a BCD switch, and thereby actually connecting it to the FPGA pin after the tri-state buffer, and the code for this one is once again input output declaration is here, and we have put only just 4 bits here. For as many number of bits that you require, you will have to put, and for a 4 bit binary switch 4 is enough. If you have multiple, accordingly you have to increase this instead of 3, as many numbers as you want, and we are going to use only the assign statements, therefore, and they are declared as wire here, and there are simple 2 instruction will do the trick. So, for example, we enable first here, and in concurrent statement is another mux here. This is the output assigned, output B is derived from either the actual DAP switch which is connected to the input, or it is forced with 0. It is forced with 0 if enable is it is in disable mode, that is enable is 0, naturally 0 will be forced onto B. This is at the time of configuring. When you configure the bit stream, this is the case normally, because when you switch on and all the FPGA pins are normally cleared, and therefore we have returned this way, and this particular code, simple just 2 codes in essence, will very easily solve the problem which we have explained earlier, and that is the end mod. We have seen this 4000 series board wherein problem is encountered. This board is shown here, and this is the Xilinx chip This is actually XC4010, and associated with this problem we have already seen, analyzed, and then seen how to solve the problem. So, next is we will see the traffic controller, a demo of the using different boards that we have already considered, namely the FPGA board as well as digital I/O card. And herein we need to connect this FPGA card to a parallel port that is shown here, and this is the parallel port connection, and from here it trails there and then gets connected to the FPGA board and right on the top here, and this is the connection there, and this is the FPGA board, and a zoomed version is available right now. So, you can see this different the main FPGA is here, and this is XCV 800 device. We have also already seen description of all the other things, and these are all the flat cable connection expander, and these cables are connected to the digital I/O card, which is next here, right here, and a zoom version you can have a look, and this that cable connection is right here, and this what we have already seen, 50 pin connection, and this is the BCD switch, it is graduated 0, 1, 2, 3, 9 and so on. Like this 8 such provision are available, and 8 DIP switches are available, push button switches are here, and now we will see the working of the traffic controller. Right now it is on, and you can see the traffic controller board here, and the zoomed version is here, and you just have a look at some of the part of the sequence for a while. The traffic controller bit stream is loaded by using GXS load here, and we have already seen this in the manual earlier, covered earlier. This is the board type XSV 800 selected here, and the connection is LPT1 parallel port, and that is what is put here, and the bit stream that you need for example traffic underscore controller, which is actually a dot bit, and we had to get this in this field by merely copying and dragging from the folder in which it is available, and this is what we have already seen in the previous designs in traffic controller, and once you have got the decide file on this, you have to load that. So, this is done by pressing this right side one button is there. Now, watch what happens while doing the load. So, you see another small window open down, and it is actually loading the bit stream here. If you see that traffic controller dot bit, immediately what did you see here, and it has been it has initialized the display, traffic controller display, starting with this is the main road, right from here left to right, and what you saw was a green transiting to yellow there, and this is this vertical road is the side road, and you can see the entire sequence. And earlier in the design we have used for main road 45 seconds green, and this has been lowered to 15 seconds in order to get a good demo here, and you can probably keep track of how much time it actually takes each of them, and then make sure that they are really working, and this will be there in one of the corners all the time that we are going to cover. Now, let us see what we have in the traffic controller, and the point here is, so this is the traffic controller which we are already familiar, and I am not going through the detailed description of the Verilog code which we have already seen earlier, and what all we have done here in this is added some more features, namely pedestrian crossing, which was given as an assignment earlier, is actually put in this code, and this is not in the demo that you are seeing, and of course blink control is also there in the 1 minute. While running through the normal sequence of the traffic lights, so you have also the provision for pressing a blink control, and PB1 through PB4 that you see is one of that is used, namely PB1. If I press this one, you just watch what happens to the display, and you can see that it is blinking. All the yellow lights are blinking as long as this is switched on. this is equivalent to switching on during the nights, blinking of the lights during night for cautious driving, and when you release, it reverts back to the very first sequence that you see there. We will see the traffic light controller code amended for catering to blinking covered in every state instead of just one state what we have covered earlier, and that is one change that has been incorporated in this revised traffic controller design. And in addition to this, we had given a assignment for pedestrian crossing that also has been incorporated in this, and so this is what is here for this control the traffic lights of a 4-road junction with pedestrian crossing. And we had earlier 45 seconds for the main road traffic, which has been amended now for 15 seconds, and side road for 10 seconds, and other things are same, namely the yellow lights for 5 seconds and blinking at 1 second rate, and this is what we have already seen. This is the road here. Before that, let us have a look at the PowerPoint presentation for the same with the amended code. So, to start with, right on what we have is the straight flowing traffic with the MG1 green, MG2 green, and while this happens, we can also allow the pedestrian to cross over here, namely PS stands for the pedestrian signal, and 1 and 2 the same nomenclature we have adopted earlier, 1 for this side road and this for 2 for other side of the side road, and S stands for the side road, and you have this signal here which is on, and when this next sequence is it converts it into yellow. When that happens, we have removed the pedestrian crossing because it is much safer before the oncoming traffic which is in S2 here, which happens to be the left turn as well as the right turn here, and corresponding signals are all lit here, and we have now left turn. This is an extra addition here, and this was already there, right, and next one is once again it will go through the yellow as far as main traffic is concerned, and that is S3 sequence. And in S4 sequence, the reverse for the same main road happens, and that is right and left traffic is allowed here in this case, and once again you can see the left indicator here, and once again it goes through the yellow sequence, in which case SY1, SY2 are on here in order because it is going to be green in the next sequence, that is SG1 as well as SG2, and that is why we provided this. In case you are not happy, you are free to change, because it is a question of changing few Verilog codes. And next one, here you can see that main pedestrian crossing is lit here, the signal is lit here, allowing the pedestrian to cross because this is going to be straight traffic. And in addition to this left, we can also provide here, in fact this is nothing but the same thing we can duplicate here also if you want this crossing. You do not need any extra signal as such for that. And next is once again an yellow traffic transition here, and after this we have S-side sequence, which will be the same case for left and right traffic from the side roads. Side road 1 is allowed here, and once again yellow transition, and in this case it is only yellow for this is given because next is going to be on this side, right traffic as well as left traffic flow as far as the side 2 is concerned, and all other things I do not have to explain here, they are naturally red, and whatever is to be done, it has been done. And as far as this is concerned, both left flow as well as right traffic signal must be on, and once again it goes through the yellow and in this sequence, and next is going to be the very first, actually next is going to be the very first sequence here, and that is the reason why yellow has been marked for the main here, and also S12 gives the blinking. Earlier it was, if I remember correctly, it was S8 state, and now it is S12 state, because we have added some more states in between, and instead of 8 plus 1, 9 states were there earlier I think, and here it happens to be is it starting from S0? S0 to S11 is a normal sequence, that is 12 sequences plus one more sequence here for the blinking. So, reverting back to the code, so these are all precisely the same definitions, etc. We are not going to repeat the thing. So, wherever there is a change, we are going to cover that, and we had a time base for 40 megahertz earlier, if I remember correct. Now, what we have is 50 megahertz, because this is what is demanded by the access board, and as I mentioned earlier, there was a divisor which we programmed, and that was in terms of 1, 2, 3 and so on, and we had put a divisor of 2. That means we get from 100 megahertz, which is the basic clock frequency, and a factor of 2 will give you 50 megahertz. And therefore, because of the board requirement, we changed this frequency, for which instead of 3999 for 40 megahertz, we need to just update it to 499. That is all the change here. And naturally, for timing also we had to change. This is for the 15 seconds timer, always one count less, as we had discussed before, and this one is 0.1 second is the time base. Therefore, the decimal point is reckoned here. So, it is actually 15 for 14.9 means 15, because this is one count less, 0, 1, 2, 3 is the count. That is the reason why one less, and so is the case for the 5 seconds, 4.9 here, and similarly for the side road you need 10 seconds, so it is 9.9, and you need for 0 through 9 it goes as far as the basic time base is concerned, which gives 0.1 second delay, and that is here, and for which we need instead of 10, 9 actually, 1 less. So, this will give you 0.1 second delay. So, these are all the declarations here. For example, left turn and or extra here, and pedestrian main, similarly pedestrian side, and similarly all left are all extra here, and pedestrian signal here. Then blink happens to be the very same thing, and once again we have IO declarations, and so once again you see this left output and pedestrian main, and then once again left for the side, then pedestrian crossing outputs, and essentially the wire happens to be the same thing, and then for timer, and once again here we had to declare registers, and this pedestrian main, and once again left side turn as well as pedestrian, they have got to be declared as reg. This is essentially the same. This is to create a 0.1 second time base, and these codes are exactly the same. You can't take it left, it is a field of view is like that. Now you can see the first okay. So, the first character is although it is appearing on the monitor, it is not appearing there on the screen. I hope it is visible on the TV, and anyway we are not really interested in the actual thing, because we have already covered these codes. So, we need not really worry about that. I am not going to describe the code, and these are all exactly the same thing, only the difference I am pointing out. For example, 45 seconds it was, and the comment is now for 15 seconds. This is the timer 2 catering to yellow lights, 5 seconds. Again, once again there is no change here. This is for 5 seconds. This is for 10 seconds here, and this is for 1 second for blinking, and so this is continuing with the same thing. Different counters are running, which we have already seen. So, this is the initialized condition, and this also is same, and wherever the extra sequences are involved, we will cover that. See, the first one is also same, and So, you have seen here pedestrian is included here, side pedestrian can cross when the main switches lights are on, green lights, and we have turned PS1 and PS2 to 1 here, and all other lights is exactly the same that we are going to see all through in each of the extra sequences that we have added. And for example, and we had to turn off unwanted left signal here, and that is what we are doing here. This is for 15 seconds timer. And notice that for hereafter every sequence you will be noticing that we have included blink state, and so that we do not have to wait till the end of all the sequences, which we had done before. And in this case we are taking at every sequence S0, S1, all sequences we are sensing the blink. And once again you can see this pedestrian not wanted here, therefore they are turned off here. Then main pedestrian is also turned off here. That was for two sequences S0 and S1, and this is S2 sequence, and once again blink control is taken into account. If blink is 1, then naturally it will go to the last state, S12 state, which happens to be the blink state, and this is what we have already encountered earlier also in the other two sequences. And in this particular sequence we have one MLT1 coming into picture as well as MRT1, and naturally we need to switch off all other unwanted lights, and including MLT2 here, and main pedestrian crossing, and again SLT1, SLT2 left traffic of the side road, as well as the pedestrian crossing for side road. So, once again for S3 we have a blink control here, and once the lights are different here. Once again you can see left flow for the main are all switched off here, including the pedestrian crossing, and the side road left also are off here, and so is the case with pedestrian crossing here. So, this is S4 state, and if you look, if you want to recollect what that S4 is, you can just have this is right flow traffic from the side main road itself. So, you can see right is allowed here, right as well as left flow from the second the main road, and all other lights are off here, and you can see this left side as well as pedestrian signals are all off here. So, S5 state here is they are just yellow transition in the same manner. So, you can see the yellow being on here and all others are off, and including MLT and SLPM, then SLT, as well as pedestrian crossing. Next state is S6 here, once again blink taken into account. This is S6 state, and here what is available is S6 is the side main traffic flow, and there is a PM here, and naturally SG1, SG2 only are alive there in that. So, you can see SG1, SG2 and PM is also there. All others are off. The side main traffic yellow lights are shown here as S7 sequence, and the corresponding code here is MR1, MR2, 1, then side 1 each, and all other lights are off. So, next sequence is S8. Once again blink is taken into account, and in this case you can see that all reds and side right as well as left traffic is on here. That is so you can see this, and next is yellow, and then followed by this side. S7 is this from the top. S9 once again blink is there, and we have seen this, and both main red as well as side red is on, and so also the side yellow, and in all other lights are off, and in this is S10 sequence. Once again blink is taken into account, and in this case main road red as well as side road red are all 1, as well as right and left are on here. So, you can just have a look at this. So, you can see this 10 right as well as left on, and all other red, and this turns into yellow here, MY1, MY2, and then red there for S11 sequence. S11 is here, once again blink is taken into account. Then here you have MY1, MY2, 1, side road red here, and side yellow 1. Is this correct? This is for S10 sequence. S11, sorry, S11. I'll just have a S11 is MY1, MY2, and SR1, SR2. MY1, MY2, SR1, SR2, and I think some problem is there in this. SY1, SY2 should be 0 actually, isn't it? This is for S11 case. I think this must be 0, right? S11, isn't it? So we will just correct this here. This is 0. This is also 0. Okay, next one is, we will just go through this, and all other lights are off. This S12 is the blink state, and we check the blink also here, and we switch off all lamps except for the yellow lights which is going to blink, and that is covered only here. So this is precisely same as we had S8 state earlier in the earlier design, and this is also exactly the same thing. We are inverting the SY all yellow lights condition so that it keeps on toggling. This is happening every 1 second I mean every 0.5 second. So you have 1 second time period or 1 hertz, and that is for all yellow, which you can see from the PowerPoint here. So you can see this here. So in addition to this, what we have is we will have an assignment for you, and this assignment is what we have done is these are all I mean timings are all programmed for the main side road traffic as well as yellow lights. What you do is you take these switches are there, SW7 and SW8, they are all BCD switches. You can program right up to 99. So you use this as input for the timing, and you have only one 2-digit setting, and in each time you want to set for main traffic delay, you can use 2 more jumpers here. For I mean in the SW1 switch, the last 2 bits you allocate for selecting which of the 3 timers that you are going to select. So 0 0, let us say you select the first main timing, and 0 1 for the side timing, and 1 0 for the yellow timing, and corresponding timing also you have to set in this BCD switch, and you can just whenever you want to put this I mean enter this, just press push button 2. So this is the assignment for you, so that a cop can change right on the field, and thank you.